Okie dokie. I think I already have it open. Yeah, I do. All right. So last time we were kind of talking about the bigger picture of our computers and starting to think about our computers in terms of its granular parts. So we started creating this list of the things that make up our computers and how those things might play together with other things. So CPU, talked about that quite a bit. Didn't talk about hard drives too much, but these are all things that most of us know are part of computers. We're going to spend quite a bit of time in here talking about memory-related things, not just your system RAM, but all the different RAMs, different memory things that are inside of a computer that we don't necessarily think about on a daily basis, but things that we maybe have heard of before related to processors like L1, L2 cache, L3 cache, things like this, how those things play into multiple core processors and all that stuff, things that are kind of off our radar, we know exist, don't really know why they exist, and things like that. Okie dokie. So we talked about CPUs, kind of history of these guys. We talked about the architecture of CPUs, how when a new CPU comes out, and actually I just had this discussion in one of my classes this morning, and I brought up the same point that I'm about to bring up now, is one thing you maybe have noticed, certainly within my classes, but I would suspect across other classes in the computer science department, that you often hear the same subjects discussed from different angles. And that kind of goes along with Dr. Locklear's grand ideas of computer science stuff, where you have these different pillars of computer science, and they're all related to each other in some way. So you can have a discussion in artificial intelligence related to CPUs, just like you can have that in an architecture class, just like you can have that in a programming class. You might be concerned about different aspects of it in those different classes, but it's still related things. So when we talk about the architecture, let me just look at the next couple of slides here we did here. Okay. When we talk about the architecture of a CPU, what are we really discussing there? When I say architecture, what's that kind of a synonym for? Go ahead.
The logic behind its logic.
The logic behind its logic. Is that a thing?
Like how it thinks, how it's organized.
I mean, I feel like it might be a thing, but it doesn't sound like it should be a thing. I'm going to say maybe. Okay, but let's see if we can get a clearer answer. It's kind of maybe a short, convenient way of talking about computer architecture, and that's a particular CPU's instruction set, right? So I'll go ahead and throw that on a slide. We've heard that phrase before, instruction set. So now when I say CPU instruction set, what am I talking about? In Littman terms, relative to how I teach CPUs. Go ahead.
The magic tricks.
The magic tricks. Okay, it's the list of magic tricks that a CPU knows how to do. Okay, that's our instruction set. All right. I have a question on an exam, in Littman terms. You just speak in circles for 20 minutes and then talk about burritos or something. It's probably worth half credit minimum. Okay, so CPU instruction set is the list of magic tricks that a particular CPU can perform when asked. Okay, does this change? When does it change?
When you get a new CPU.
Likely when we get a new CPU. So we went back to our CPU list here, and we go all the way back to these older ones. Now, our CPUs today are backwards compatible with these. I would assume to a point, there was for a long period of time, our modern CPUs are going to be backwards compatible with older CPUs, but there's probably some line in the sand that's been drawn a couple of different times where it's like, look, you are not going to be able to run this software on an older architecture. Just don't do it. It's not fast enough anyways, and it doesn't have the magic tricks, something like that. But in general, there's an effort made to make the newer CPU backwards compatible with a previous CPU, and then just either update existing magic tricks to be more efficient or something like that. Now, when we think about a magic trick, I think it's kind of important for us in here. Let's kind of unpack this a little bit. What is a magic trick?
Something we just don't understand how it works yet.
But I want to think about it in terms. I mean, somebody made this, right? You got some smart people over at Intel or AMD who's creating these processors, and that's just our desktop processors. There's all sorts of different processors that get created. Somebody's creating these things, and they're the ones implementing the instruction sets. As I call them, these individual magic tricks. What's the nature of a magic trick? How is it implemented? What is it? I think somebody last class mentioned something about like logic gates and stuff like that. That was you, right? Yeah. So I think I mentioned something along the lines that we can kind of think about these the hardware components of our CPU as almost like a computer program written in hardware. We had a discussion last class about firmware. I think Alexis came up with the firmware answer, right? But kind of talking about where hardware is really fast but inflexible, software is super flexible but less fast. Where's the happy medium type thing? But our CPUs are, at least as of right now, pure hardware. So somebody's kind of creating these computer programs made out of hardware, and the program is our magic trick. Or we can almost think of our magic tricks as kind of like a function, where you give it some inputs and it spits out an output. All right, so magic tricks we can maybe think of as a hardware-based function or method, however you want to think about it. Okay, there's some number of inputs and some number of outputs. Typically, when we think about functions, we think about single outputs, but some more modern languages do allow us to have multiple outputs. And even when they didn't specifically support multiple outputs, we could have multiple outputs by returning an object that has multiple things in it, right? You want to return 6 things. Here's an object that has 6 things in it. Return the object. Okay, so a magic trick is effectively a function built in hardware. So it would be possible when the latest, greatest CPU comes out that some magic trick that did exist last year has now been maybe reimagined or re-implemented for efficiency or something like that. And provided that the inputs are the same and the outputs are the same, the implementation in the middle shouldn't necessarily matter. Newer, or an older software application can use that newer magic trick that's called identically. And as long as it's getting an expected result, it'll work. Even if the Intel people made that magic trick 30% faster or something like that, as long as they kept the two sides. And that's actually a topic that you talk about in the software engineering class, right? When you start thinking about, a large software application. So in this case, we're talking about a large hardware application. I'm not sure application is the right word, but whatever. But a large software application where you have a team of people working on something. And I mean, it's one thing to have 12 people huddled around a computer all working on one problem, but that's not as efficient as having 12 people working on 12 separate problems. As long as those problems are separatable, divisible. Divisible is probably the better word. Separatable sounds better. Separatable. How come I find myself more entertaining than you do? Is that a thing? Some of you just want to you look like you want to take naps. I don't get it. Okay, so in any case, one of the things you talk about in software engineering is this exact same concept where you have your project manager or you go through your software development lifecycle, whether it's Scrum or something like Waterfall, whatever, and you're effectively driving down into this idea of here's the functionality, and these two functionalities are reliant on each other. So these two people are going to work on this functionality. These two people are going to work on this functionality. We're going to divide them into functions. This function over here, we don't care how you write it. Well, we might care a little bit, but it needs to have these two inputs and it needs to provide this one output. So as long as we can, it's functionally compatible with what we're going to plug it into on the other side. As long as your solution is accurate and reasonably optimized, we're going to be fine with it. that type of thing. But that's a really important thing. It's kind of like going to Home Depot because you need some part for fixing something at the house and you get the wrong size screw. You had to get the right size part that was compatible with the thing you were using it for. Okay, that's kind of what we're talking about here, and the same thing's true when we deal with CPU architecture. It's just scarier sounding because it's not something we sat there and wrote in the software, where if somebody screws up, you go back and, a roll back to last week's file or just a couple of lines deleted and rewritten and it's fixed. All of a sudden you have 5,000 processors that have come off the line and they're expensive, and all of a sudden it's like, oh, well, this doesn't work because there's a bug in this updated magic trick or something like that. Okay, so one thing we might see in newer processors is an updated implementation of one or more of the existing magic tricks. Now, put this thing in here. Continue with my jargon. Why update a magic trick? If it already works, why make changes to it? What are some other goals that we have in computer architecture today?
Make it better.
Okay, tell me about better. We walked into that one. Okay. I don't disagree with you. Just tell me more. What does it mean for a processor to be better?
Usually for people, it means to be fast. Fast at home or memory.
Okay, so maybe faster.
Energy efficiency.
Okay, what do you mean by efficiency? How can something be efficient? Now, this is all perfect. These are the exact words we want to use because we want to recognize that those words mean different things to different people, right? What does it mean for something to be efficient?
To save energy, because now most of the big devices are mobile devices and they're operating on battery.
Yeah.
So they kind of make it as small as possible and as light as possible, and energy efficiency.
Yeah. So we said efficient. Now, we have the luxury relative to the past. We have the luxury today where our computing power is pretty fast, right? So we might be able to say, you know what? To make this magic trick efficient, I'm actually going to make it slower. It's still fast enough. In fact, maybe nobody would ever notice. But I'm going to make it slower because by making it slower, changing how it's being done, I can save a lot of energy. And as you mentioned with mobile devices, when we're running off of a battery, if you can save 30% of your energy and only give up some speed and maybe not even noticeable speed, we're going to consider that to be better.
Well, most people won't be able to notice the speed
That's
difference.
it. So, but the point is, we just created a scenario where making something that used to be faster, slower, but saving memory or saving energy is actually better to a certain audience, right? If you're plugged into the wall and you don't care about your power bill, would you ever slow anything down?
Yes,
Tell me why.
because less energy means less heat.
You don't care about your power bill. Okay. Tell me about the heat thing.
Well, when you expend electricity, the resistance that you inevitably get creates heat. And so you want to minimize heat as much as you can.
Do you?
Well,
Do you want to minimize heat as much as you can, or do you want to minimize heat to the point where you don't have faults in your hardware?
to the point where you don't have
You don't care if it's hot in there as long as it still works.
Right, I guess the only degree that matters is the one that breaks it.
Well, what do you see in a lot of server rooms? You see big air conditioning units, right? Just crank it up. That would be just a power bill, right? Yeah, burning fossil fuels, whatever, all this other bad stuff. But the point is we'll make it cold in there somehow. And we're not giving up speed. So generally speaking, if we're talking about not running off battery power, we're talking about being tethered to the wall. We have all the electricity we might need. Okay, and somebody else is paying writing the check to the power company, and we could just throw 5 more air conditioners in here. We wouldn't slow down something just at the cost of energy savings if we're not relying on a battery. So in that situation, we would consider faster better. Make sense? So better is all relative. Efficient is all relative. All right, so we might say sometimes slower and more power efficient is better. Sometimes faster, and who cares about power is better. And then there's probably shades in between, right? All right. What else about efficient? Other than efficient, go ahead.
Oh, other than efficient, like security vulnerability, like what's it called? Meltdown. Like to update the CPU architecture because.
Yeah. So there might be something that functionally works, but it might open the system to some kind of attack or something like that. If you're able to grab onto that particular magic trick and there's issues with it, you might be forced into a situation of maybe slowing it down or becoming less memory efficient at the cost of, hey, now it's secure where before it wasn't. It doesn't matter how power efficient it was, rather, or how fast or slow it was before, if it's basically this giant unlocked door in your system. All right, so security, certainly, especially today, kind of a big deal. All right, what else?
Like more dependable, like you can rely on it more often. Also, you can probably, like with newer, if you're like designing a new processor, like you can add, like, let's say 2 new magic tricks to replace like 3 or more older ones.
Yeah, so really you said 2 different things there, and both of them are good. So possibly bugs. We have this whole thing that 99.9% of software applications have bugs. The same thing we can say is true about hardware applications. The hope is, since at the processor level, when we're building these tiny magic tricks, we're doing something very, very, in the big scheme of things, simple. 2 inputs, 1 output, and it's an AND gate, something like that, where we can probably say it's relatively bug-free. But as we get to these, super magic tricks that are trying to accomplish a little bit more to optimize certain things that are commonly done on our computers or something like that, there may be bugs in the system where maybe under a very certain situation, a processor faults, where maybe you want to fix it from that perspective. Now, the other thing you talked about is the addition of new magic tricks. So we might have an existing magic trick that does X, and perhaps, maybe let's say it does X and Y. And perhaps we decide, it would actually be beneficial to have it do X, Y, and Z, because those 3 are commonly used together, something like that. So you might create a brand new magic trick that does all 3, hence making it quicker because you're only making 1 system call rather than 2 system calls, or 1 instruction call versus 2 instruction calls. Save a little bit of time there. But does that mean you can take away? Let's say you determine in modern programming, or modern programming is fine, that the 1 instruction X and Y are never called by themselves, or are rarely called by themselves. They're almost always called with the X, Y, and the Z. So moving forward, new software applications might take advantage of the X, Y, and Z combined magic trick. But old software won't be able to do that. It would have to still make the 2 separate magic tricks. So you can make the argument, do we remove a magic trick from a CPU? Because if you do that, then all of a sudden your brand new CPU isn't compatible with last year's software.
What if it's like a decade old and you've been wanting to get rid of it for a while?
Yeah, so that's where we decide where's the line in the sand. At what point do we say that software that was written before year whatever can no longer run on our new stuff? We're not going to keep around a bad magic trick, or a magic trick that is antiquated. Maybe that doesn't necessarily mean bad, but whatever. Just to make some software that hardly anyone is using continue to work. We're going to draw a line in the sand somewhere so that we can move technology forward. We see these moving parts where those are just tough decisions. Go ahead.
So it's kind of the same thing that they do with operating systems. Like certain computers can do certain operating systems, almost all the way back to Vista. Some do not.
Yeah, and we see a partial solution in our newer operating systems where the operating system might as a whole make the decision that we're going to take away this compatibility. But then they've added a secondary system for compatibility mode, where you can say, look, if you want to, this application used to run well in Windows 95, and it doesn't directly run well in Windows 10 because we've removed some stuff that it used to rely on, we'll give you this compatibility mode, which probably isn't the best performance in the world, but given the fact that it's a Windows 95 application and you're probably running some pretty good hardware relative to what they had back then, you probably won't notice. We'll allow you to kick this into Windows 95 mode and run it through that filter as a special case, rather than keeping all that extra bloat in there for the common case of Windows 10 applications, that kind of stuff. Yeah, so we see it at all sorts of different levels, exactly. All right, so generally speaking, when we're releasing a new processor, we are adding new magic tricks, which may be completely new or maybe are combinations of often used magic tricks that are often used together. Because even just taking two magic tricks, making no changes to them, but incorporating them together into one magic trick will increase performance, because now you only have one instruction call instead of two. That's a perk. That's a benefit. And if you have the room on the processor, and what do I mean by that? What do I mean by room? So raise the hands again. How many of you have built a computer somewhat recently? Most of you have had 175. So you built a computer in there, right? So you had a processor, and what was the size of the chip? About that big, something like that. And that had multiple cores on it. We'll talk about that shortly. But how big do you think processors were 5 years ago?
Okay.
Same size-ish. Yeah, I mean, they change pinouts and stuff like that sometimes just to make you go buy a new motherboard. I mean, there's probably more to it than that. There's some other advances. But generally speaking, the physical size of our processors have not changed more than a tiny, tiny, tiny bit over the last 20 years. Same size chips. All right, but the amount of stuff we're shoving into that same footprint has changed. Okay, we keep talking about, let's go here. Sometimes when a processor comes out, you'll hear them refer to it like the current chips are 9 nanometer tech. I think it's 9 nanometer. I think this one's just coming out. Don't hold me to that. But whatever. What are they referring to when they say 9 nanometer or 12 nanometer or 15 nanometer? Go ahead.
They're referring to the size of the transistors that they use in the circuits.
All right, so now when they're creating a prototype for a processor, it's going to be this almost back to our old discussion in the programming classes about object-oriented languages versus procedural languages. When I talk about you might have a telephone sitting on this table, this is giant pile of wires. You can technically create an Intel Core i9 processor that is just a giant pile of stuff. Okay, because they haven't, that's the prototype for it. They're making sure it works right and stuff like that. They just have all these little magic tricks through gates and stuff soldered together, and we're going to lay that magic trick there, and they could take this whole room. They probably would take this whole room for the size, the number of magic tricks that are on the latest, greatest processors. But once they have that all done, then they're going to convert it into a production model where they're going to actually use very large scale integration, VLSI. And that's kind of the overarching technology. There's some lower level tech, like evolutions of VLSI. So very large scale integration effectively says we're going to take that pile of wires that's in this entire room, and we're going to come up with interesting ways of, with low fault tolerance to get it into this little tiny package. Okay, and unfortunately, humans are not going to be involved in that process because our fingers are too big. All right, so no longer are we sitting there with the soldering irons and stuff like that. And I used to do soldering iron stuff in this class, but now with my shakes, I just get solder everywhere because I have my tremor in my hand. It's a waste of time. It's kind of funny for the first year, but after that, I was getting on the laptop and all sorts of stuff. But the punchline is that's not even how things are done anymore. If you're a hobbyist and you're working with like a Arduino or something like that, and you're creating a little logic board to do some stuff, and you want to have this little LED light flick on or flick off when something happens, and we might even do a little something like that. You solder these couple things here, and you have a little battery, and like, okay, I'm going to power, light comes on, no power, light goes off. Go through an AND gate or something like that, and you can kind of see the equivalent logic gates that we've been used to from just Boolean logic with if statements and programming. We can see it in hardware. But this nanometer technology, this has to do with when we go to print a circuit board. And it's a little bit more complicated than that with processors. They're doing it even at a lower level. Let's call it kind of a microscopic level. How close can we put things together in terms of size of transistors and the silicon base that we're working with before things start interfering with other things, or before heat becomes a larger and larger and larger problem? Make sense? So, last year it was 10 nanometer, and they said this is as good as we can get. And then this year it's 9 nanometer. We've gotten a little bit better at making them a little bit smaller and a little bit closer together, and still not catching fire upon boot. And then one of the things we do see, though, is as our processors get more and more complex, as this number goes down, the 9 goes to a 5, goes to a 4, eventually we have 0.2 nanometer. I don't know if we'll get to that, but that'll be funny. One thing you do notice when you look inside, if you've been building a computer with these, is what has changed along with these processors becoming not necessarily having faster clock speed. We talked about that a little bit last time, but more cores, more stuff shoved onto them. As we have this more, smaller nanometer type thing, we can get more magic tricks on that same chip, right? So that's how we evolve that processor. But what has gotten bigger inside of our computers? Processors remain the same size. More stuff fits onto it as we get this nanometer number down. What's gotten larger? Well, they've definitely gotten larger, but for a different reason. Heat sinks. Man, you got some impressive looking heat sinks these days. There was a time where the heat sink for a processor was this little tiny thing. It didn't even have a fan on it. Then they put little fans on them. And now you have these heat sinks that are just like a tower of metal with like copper pipes going all throughout it and stuff like that, with like fans on both sides, just doing everything it can to move heat away from that processor. I mean, where you have to get a special case for a motherboard to fit in, that the heat sinks will also fit in. And then we have liquid cooling and all this other stuff that's going into it too. So we're at the point now where we're going to say, look, you're going to be inconvenienced. The more stuff we shove in these processors, now all of a sudden you have heat dissipation requirements that are expensive. A cooling fan for a processor used to be $5. They're not $5 anymore. They're a lot more expensive, especially for like server chips. You might spend $120 just on your heatsink and fan. Expensive stuff. All right, so our technology is getting better and better and better at shoving more stuff into the same space. Now, we maybe also are getting better and better and better through optimizations at reducing the heat from those things now being closer together, or us upping the clock speed or whatever it is in that same space. But we're also kind of covering our bases by having more and more cooling requirements for those same things. And this is all kind of the punchline of what we were talking about last time with clock speed, where we kind of pointed out that if you've been looking at computers in the market for buying a computer today versus buying a computer 6, 7, 8 years ago, the clock speeds have not necessarily changed drastically, right? Generally speaking, they've stayed the same. In some cases, they've gone down, because the higher the clock speed, the more heat you're going to have in the same architecture. So if our architectures just keep getting more and more complex, even if we keep getting better at optimizing them for heat and things like that, you start ramping up the clock speed, it's going to start getting hot again. Make sense? So we got this constant game of checks and balances that we're trying to play. And then we have to ask ourselves at the end of the day, what's fast enough? Or what's the answer to that?
It depends.
Depends. Once again, it depends. Okay, I think I used the example last class when we're comparing. I think I was mentioning the MacBook Air, like an 11.6-inch MacBook Air I once had, and then at the same time we had a Mac Pro with 12 cores in it, and just a beast of a computer, relatively speaking, to the MacBook Air. And when you're checking your email, they were probably the same speed, but I felt like the Air was faster for those kind of tasks. Where the certainly was faster to do it because the Air fit in my pocket, but the almost fit in my pocket. But the obviously the Mac Pro was far, far, far more capable for different tasks. If you were trying to convert an hour-long movie on a MacBook Air, it would have taken a long time. Where that same movie on maybe it would have taken an hour. That same movie on that Mac Pro maybe would have taken 3 minutes to convert. So that's where you saw the advantage of the multiple cores and things like this. But we haven't necessarily noticed a drastic change in the high end of the clock speed. One thing we do see today, though, is we see turbo, right? Turbo mode. So you might get a computer that has like a 2.2 gigahertz processor, turbo up to 3.6 gigahertz or something, right? So that's saying, look, go ahead.
I thought the turbo button was supposed to clock down the CPU to be better compatible with older software.
The turbo button?
Yeah.
We're talking about turbo button. I'm not talking about like a button on the computer. Like the processor has built into it a magic trick that allows it to ramp up clock speed. Yeah, and it's for short bursts of heavy computation. So it allows you to accomplish more in a short period of time situationally at the cost of heat, wear and tear probably. I don't know if anymore we really have an issue with processors actually wearing out. We're usually replacing them. Our manufacturing process is pretty good now, so we're usually replacing these things before they wear out. Even the same thing's mostly true with hard drives. One of the things we have with mechanical hard drives for a long time, especially in server farms, is they'd eventually wear out. They have moving parts and things like that. Even now, we're moving away from that more towards solid state or similar technologies. To have a part actually wear out from just overuse isn't real common. Usually it's going to be something related to heat or something like that because you weren't properly cooling the area. But yeah, so these processors that have kind of a turbo mode that allows the processor to scale up to a higher clock speed situationally to accomplish more in a very short period of time. It's not something you want to be running at that speed a majority of the time. Now, that's kind of compatible with this notion that most of the time we don't need the top speed. If most of the time we're using our computer and we're just using it under kind of normal, check your email, browse the web, stuff like that, the difference between a clock speed running at 2.8 versus 3.2 is not going to be noticeable to us because we're only using a percentage of what our CPU is capable of doing at that point in time anyways. But if it gets under heavy load, that CPU can ramp up and it'll measure the heat and ramp back down when heat starts becoming a problem. But it'll allow you to kind of get through those, almost like when you're like mowing the yard and you get to that really tough piece of grass that's been growing forever because you try to get really close to the house and you've been lazy, you don't weed whack, and you see how close can I get the lawnmower to the house. None of you play this game? Yeah, it's like, oh yeah. It's even better when it's a riding lawnmower. Because how close can I get with a riding lawnmower to the house? Then my wife comes out, she's screaming at me. My neighbor comes out and he's screaming at me because he wants to know why I stole his riding lawnmower. I'm not gonna push a lawnmower. He's yelling at me about weight limits and stuff like that. It's a John Deere, it's fine. I hate that guy.
Pretty sure pushing lawnmowers is assault.
Pushing lawnmowers is assault?
Yeah. They're nice people,
Oh, there's a pun built in there. Yeah, so in any case, you get to this grass that's like super high because it hasn't been cut forever. And it takes some extra juice to get through it, right? Or if you don't use the battery operated weed whacker for that. You got to get the gas one out to get through that stuff. So the same thing's true here with turbo mode. You're using it for those situational things where your processor is under heavy load to get through it and move on to the kind of the normal tasks. And we see the same model represented in, we talked about it last class, represented in our mobile devices today, where we have a couple of we have multiple core processors in our handhelds, and anymore, we don't have all the cores being the same. We have typically two higher performance cores, and then two or more efficient, power efficient cores, which is a nicer way of saying slower processors. So we use the heavy duty ones when something needs to get done and it's worth it at the cost of battery life, and then use the other ones the rest of the time when you're up, checking your email or something like that, where this isn't a massive computational problem. Your bottleneck in those situations is probably your internet connection. How long can you download? Does it take to download the attachments? That kind of stuff. All right, so those are the things that play into clock speed. This technology for, how small, this just has to come down to how much stuff can we fit in the same footprint, and at what point do we decide if we need to fit more stuff in there, if we need more magic tricks, and we can't put any more in the same footprint. Is it worthwhile having a bigger footprint? Do we come out with a bigger processor? This is the current thing we're fighting. And then what's our solution to that war? We can't fit more stuff into a single processor. So now what do? Is we start putting more processors onto the same piece of silicon. That's where we start getting dual core and quad core and octa core processors. We have they're actually not in a machine that works yet, but we have these AMD EPYC, which is the server side of AMD's Threadripper technology, that have the processors we have are 24 core per processor. We have 2 of them, so that's 48 cores, and each one has 2 logical cores. That's done through something called pipelining that we'll talk about in here. So that means we have effectively a 96 core setup in a single machine. Well, that's only going to help you in very specific problems where you can divide up the work, right? But punchline is, rather than making those processors bigger, and they are physically a little bit larger, and rather than putting more stuff into more magic tricks into a single CPU, which we have a heat issue with, now what we're going to do is we're going to take advantage of our smaller technology to keep the same level of magic tricks into a single processor and get more cores onto the same footprint. And then make sure we put a giant heatsink on that to cool it. All right, so what have we done now? Instead of making processors faster, instead of making processors able to do at least tons more, now we're putting more processors into the same footprint. That allows us to kind of get through certain problems that are divisible, where the labor is divisible. Make some sense? And now we get then into this world of how many cores is enough cores? Well, for most of us, a quad-core processor is probably sufficient for everyday use. Chances are you're not going to be doing more than 4 things simultaneously that you have a high desire of max throughput. Because keep in mind, it's not that your computer can't multitask without multiple cores. What did we do when we had 1 core? Let's go right here. Single core CPUs. Those used to exist. Has anybody in here had a single core CPU?
Pentium ones?
It depends how far back you go. Yeah, most of the Pentiums were single core. Even the first core processors, you had the Core Solo, which was a single core processor, and then you had the Core 2 Duo, which was a dual core. Those were kind of the early ones. So, but does that mean that when you had a single core CPU, you can only do one thing at a time? Sort of a trick question. Go ahead.
Technically, but it acts like it's multiple things.
Yeah, so the answer to my question is yes, that does mean you can only do one thing at a time. So with a single core processor, you can actually only do one thing at a time. But reference the operating systems class, where you talk about scheduling for that CPU, and you talk about here's the 5 applications that are all fighting for CPU time. What are we going to do? We're going to rely on the fact that our CPUs are pretty fast, and we'll let each program get a little time on the CPU, and then context switch out to another program, which is additional overhead. But the hope is this is happening so quickly that the end user thinks all of those things are happening at the same time. That's an easier thing to do when you have more than one core, because then you can schedule across the 2 cores. So then from an operating system perspective, we say, well, now scheduling, the job of scheduling for the processor is now more difficult, because now I'm scheduling for 2 cores, or I'm scheduling for 4 cores, or I'm scheduling for 48 cores. When does it stop? So the operating system then becomes more complex, because you have to be capable of scheduling for more and more and more and more cores. And the end user are what we're doing with our computers from a normal user perspective on a daily basis is not drastically changing. Think about how you use a computer today versus how you used a computer 2 or 3 years ago. It's not a drastic difference. We might have specific differences in terms of like video rendering and stuff like that, where we are relying on maximum computational throughput. But for us writing our papers and checking our email and browsing the web and doing homework and things like that, our patterns today are not significantly dissimilar to what they were 2-3 years ago, right? So we don't really have this necessity for more and more and more cores for our consumer-based computers. Yet, if you're somebody who's out to buy a new computer and you have enough money, and money isn't the issue, might you be tempted to buy the computer with more cores versus the computer with less cores just because you think it's the better computer?
Yeah.
Yeah, absolutely. When actually it might be the worst computer, especially if it's a laptop. You very rarely do they brag about how great the battery life is on the laptop that came out that's running the latest, greatest desktop processor, because that processor is using a lot more juice. You don't see Apple bragging about their laptop running the Core i9 processor, especially not after they got called out for throttling it, slowing it down. Now they had to speed it back up, and now the battery life, I think, is 15, 20 seconds, something like that. So I say plug it in. Just you're gonna want to plug this in. It's more than 15 seconds, but it's not that much more. Not as much more as it should be.
Didn't the MacBook Air have a battery life of like 12 hours or something?
Yeah, situationally. Yeah, I think the bigger MacBook Air might have even been longer than that, but yeah, something like that. Yeah, like because they were talking about it's geared for travelers, so you can watch, I don't know, like 12 or 15. It might have been like 15 hours of straight movies on your MacBook Air on a overseas flight, something like that. But now all the overseas flights have the entertainment centers built into the seats in front of them, so it's not an issue now. But that was the thing. And what did they have in them? They had, when I had that 11.6-inch MacBook Air, it had a Core i7 processor in it, but it was low. It was like a 1.7 gigahertz one, so it was low power. And it would clock down when you weren't needing it. Had no moving parts, so it wasn't giving off very much heat. So everything about it was about battery life. And even though the thing seemed really small, if you were to open it up, I think some one of the Tom's Hardware or something like that did. It was like something like 96% battery. The computing part of it was like this little tiny, what looked like effectively a RAM chip, because the entire system was on this one little board. You couldn't upgrade the RAM. The RAM was soldered on there. The solid state hard drive was soldered on there. They didn't use separate parts. They just soldered everything together and stuck it in the upper left-hand corner of the thing, and the rest of it was a battery. Go. And that's kind of the thing with this is the Core, the Note 9. This is a 4,000 milliamp battery in it, which is even bigger than what they had in the Core 7s, which were the ones that were exploding on the airplanes. Yeah, so things could get exciting. But this is the fight we have with technology. How fast do we need something to go? And the answer is fast enough. Even though from a consumer point of view, faster is always better. That might be a simplified way of how we naturally react. That's not always the case. All right, so single core CPUs schedule by OS for multitasking. Ooh. multi-core CPUs scheduled by OS at a higher complexity for multitasking. So you don't, if you have a dual core processor, you don't get twice the performance. It's a diminishing returns type thing. You know, you get 1.8 times the performance, that kind of stuff, because the more overhead you have for scheduling for these different things, the worse it is. And when you took the operating systems class, you know, you would have talked about things like scheduling for dual and quad core CPUs. You know, one of the things you run into is this idea of if one task is reliant on another task, you can't have them running simultaneously on two different cores. There's a lot of decision making that goes into which tasks do we allow to get in line for a CPU, because they might not be able to be processed yet, even though we might have an available core. Make sense? Much harder problem to solve. That's why our earlier operating systems were the easiest ones to write, the ones that didn't even support multitasking. Hey, human, you pick what program you want running right now, and I'll run that one. You're done with that one? Close it. Then I'll let you run another one. Made the operating system significantly less complex. All right, so multi-core CPUs, that's what we're used to now. We rely on our operating system to do a lot of the heavy lifting. We talked about benchmarks last time. That's kind of all related to what we're talking about right now, where you can't necessarily look at a benchmark and say, okay, one thing has a higher benchmark than another thing, therefore it must be better. Goes back to what does better mean. All right. We just talked about number of core stuff, so let's skip that. We talked about hardware versus software stuff. All right, then we were getting to ARM processors. So to tell a little bit of the backstory here. Who makes CPUs? From our perspective in here, what are the two companies that make CPUs in our world?
Acorn.
Acorn.
Who are the two companies that make CPUs in our world? Intel and AMD. All right, so these are the big ones, and what I'm really talking about here is our desktop CPUs. We get in a whole new world when we talk about mobile. In fact, our new world is mobile. You know, we're not seeing drastic changes in our desktop CPUs. We're actually seeing changes in the way we use desktop computing. We're seeing those crossover machines now that are half tablet, half laptop, and actually kind of an interesting win from anybody in here. Have a Apple or a Microsoft Surface Book? One person? Yeah, so Microsoft hadn't had a win in a long time. That's been their first win for a while. It's not cheap. In fact, that's maybe where they went right with it. I mean, so often we've dealt with this battle where Apple has been the company that has the super expensive stuff, and then everybody else is looking at, hey, we're not trying to compete with them at the design level, but here's something that's a similar performance for ninth the cost. Well, you're in a pretty similar cost boat if you're looking at the high-end Microsoft Surface versus one of the higher-end MacBook Pros. I mean, we're not talking drastic cost differences. You probably can spend more on a MacBook Pro if you just max everything, but the Microsoft Surface books have been really well received, and it's kind of the first win Microsoft's had in a long time. They've gotten boring on us, haven't they? Microsoft has become the new IBM. Back when Microsoft was just starting off, IBM was the cool kid. How many of you think IBM is cool? We don't think of IBM as being cool. You think it's like, look, you should come to class wearing like an IBM hat. You don't see people walking around with IBM hats and IBM shirts, and you don't see that. It's not that IBM is bad. They're not cool anymore. IBM was, their day in the sun was in the past, and now they're just the stalwart, good company, knows how to do good technology business, knows their place, right? They're servers and I guess now Watson. So they're big into AI. So they might have another day in the sun now with their AI stuff, because, certainly IBM Watson has the coolest name of all the machine learning things, right? I mean, who cares if it's even, better or worse than Amazon's machine learning stuff? Amazon's just Amazon ML machine learning.
Doesn't Google have like DeepMind or something like that?
Yeah, but even that doesn't sound as cool as Watson. Better than Amazon ML. Yeah, so it's going to be this race to who has the coolest name. And it might not even be true artificial intelligence under the hood. They might just have like some dude named Chuck just sitting there at the microphone. It's like, look, people have pretty low expectations of AI. So as long as, we have a real human here who's willing to just sit in this chair, it's got to be close.
That's what Amazon MTurk is.
MTurk? I haven't heard of this.
Mechanical Turk. It's like they simulate like mechanized, automated processes by just saying, "Hey, we'll pay you 20 cents if you do this small thing." And they do it with a bunch of people.
It's actually it is a human doing it. So they're actually just using a workforce to accomplish artificial intelligence, but it's really just taking advantage of people.
Yes.
That makes sense, yeah.
Kind of.
It kind of makes sense, or
It's for what the AI can do, like reading receipts that are.
I got it. It covers the gaps.
Things like that.
Yeah. I had never heard of that. That's interesting. So they make their AI more complete by noticing its holes and plugging it with people who are willing to work for low wage.
Mm-hmm.
Is it? Do I even want to ask what country they're doing this in?
Anywhere.
just anywhere that
You can just sign up for it.
really?
Yeah.
I've honestly never heard of this.
Yeah, you can just go to the website.
And what do you just like check in for your shift?
No.
You just say, I'm going to work at my computer for these 4 hours, and during those 4 hours, things just pop up, and you have to say, type in what this receipt says.
Yeah, it's like a little bounty system. So the task gets posted, and then you say, all right, I'm going to do that task. And so it averages out probably to about minimum wage.
So really, nobody who has a computer has an excuse to not have a job.
Yeah.
Correct.
Because there's no hiring process. If you sign up, you're in.
Yeah.
Pretty much.
That's actually a pretty good idea. What I'm really trying to figure out here is why hadn't I heard of this?
Not many people have to.
Part of their Amazon One search.
Well, both of you have heard of it. Typically I try to stay up on technology quite a bit. I spend at least an hour a day reading tech news.
It's not new
Man.
at all.
So I missed it at some point.
Yeah.
Seems like they only operate in about 30 countries.
Only.
Now take that list of countries and then compare it to the 30 most populous countries in the world and see how those line up. They got to be operating in China and India.
What's the incentive if you just give random answers?
Well, maybe they cut off your account.
You don't get paid.
Yeah, I think they have a verification process.
They have other people in the system are verifying your stuff, so they have multiple points of failure. So it's almost like a blockchain type thing where you need to have 10 lazy people in a row who just happen to be selected in that process to cheat the system.
There we go. It's analog
They don't
blockchain.
need all of China.
Hmm.
Only in Hong Kong.
Which has different laws in mainland.
Yeah.
And they're not in India at all.
Really? This almost sounds ethical. Interesting.
What was the thing?
Amazon.
Working at home?
Yeah, that's all he hears. I can work at home in his job. So it's called MTurk.
Yeah, mechanical Turk.
TURK.
Yep. Like an auto.
www.mturk.com.
MTurk.com.
Wait, is that the one where you do surveys for Amazon?
We just had a 10-minute conversation about it. What were you doing over there, dude?
Reading.
Go back and rewind the video. You're filling in the gaps for Amazon's AI stuff.
Oh, okay.
All right. So who makes our CPU? So historically, we look at Intel and AMD. All right. So these guys make our CPUs. Now, I'm going to go ahead and I'm going to throw IBM in this list. IBM's made CPUs for a while. I'm going to put another couple companies in here. We're going to say Sun. That's really it. For Motorola, I'm going to put it in here because that was the PowerPC chip, and the contract ended up going primarily to IBM before it finally failed. I'm just going to leave it at that. This covers enough of what I want to talk about. All right, so for a long time, these two guys, Intel and AMD, were what would be considered historically called IBM compatible. So in the early days of our modern day PC, they were made by IBM. So they're considered IBM computers. What we call a PC today, 20 years ago would have been called an IBM compatible computer. Make sense? That's, that we just forgotten about IBM. They're not important anymore. But both of these guys were creating processors. Intel was kind of, let's call it the industry leader in it, and AMD was kind of the upcoming company that was trying to, find their niche in there. And early on, their niche was cost. An AMD processor was a lower cost processor, and they would make the argument that it was at the same price point a faster option than Intel. So, at identical price points. Not that their fastest was as fast as Intel's, but if you were paying $150 for a processor, AMD's $150 solution was faster than Intel's $150 solution. Something along those lines. All right. Now, IBM Motorola, these guys made these processors called PowerPC. Motorola also made other chips for other things, but I'm talking about the desktop world right now. Yeah. So when we talk about PowerPC processors, what am I actually referring to? Early Apple computers. Early Macs. Not early Apple computers. Early Apple computers would have been running on Intel. So it really was early Macs. So PowerPC.
Also the Wii.
The Wii didn't run on a PowerPC. No.
Yeah. Wii and Wii U were
prove that. There's no. PowerPC was dead by then.
All but.
Nobody was making it. They might have been running on RISC processors, but not PowerPC. Schrammel will get you a cookie if you're right on that one. Okay, early. Was he even listening? Schrammel, you better start finding. He might be right. You better start finding a source. You got to find a source for cookies. Look, I'm trying to find where it says it.
Let's see, right there.
CPU. What year did that come out?
2007.
What year did Mac OS? What year did Apple discontinue Intel? Look that up. I'm sorry, discontinue PowerPC. What year did Apple adopt Intel?
2005.
Yeah.
So this is 2 years after Intel's purported death, or PowerPC's purported death. You have PowerPC chips found inside of, maybe there's just a bunch of extra chips.
And the funny thing is that in 2011 or 2012, on the Wii U, you still have a PowerPC chip.
Well, that's interesting to me. So Schrammel, you got to get him some cookies at some point. I don't make the rules. All right, so we had this chip called PowerPC. For all intents and purposes, we're going to say that this guy died. This is early Macs, and we're going to specifically say this guy was a RISC processor, a reduced instruction set architecture. Whereas Intel and AMD were IBM compatible. Really, AMD was an Intel compatible processor. So Intel architecture is an open architecture, not reduced instruction set. They would move towards more magic tricks to have more granular control over the instruction set, versus reduced instruction set would say, we're going to have less magic tricks. We're going to try to identify, I want to put this in words rather than me just babble crap out here. Call this instruction sets. All All right, so we have, what is it? IA. That doesn't look right. I'm just going to call it open architecture rather than butchering. It'll pop into my head at some point. So open architecture, these were Intel. And then we had RISC. That's a board game. So RISC, RISC. This was PowerPC historically, as well as some other ones. Sun Spark chips were also RISC, but let's just use this as an example. So Intel open architecture. The premise of these guys is more magic tricks for more granular control for low-level languages. So there's our overlap with programming stuff. PowerPC, this is less magic tricks for less granular control for low-level languages. Now, what's a low-level language again?
Assembly.
Okay, that's an example of a low-level language. What is a low-level language?
A language that has a very close relationship to the actual object code.
One-to-one relationship. Who said that? Charlie? See? Charlie watches my videos. But you're right. It is a very close relationship with the CPU. In fact, it's exactly a one-to-one relationship with the CPU. So every one instruction in like assembly language is equal to exactly one magic trick on the CPU.
Well, I don't want to discount a 1.5 to 1 relationship.
A who?
1.5 to 1.
That actually, in some ways, might be true for RISC processors. No, I don't think that's fair either. But there might be a connection we can make there. All right, but our low-level languages have a one-to-one relationship with the CPU. So if we're using an Intel processor where we have, let's just use hard-coded numbers here. We're going to say an Intel processor has 100 magic tricks as our example, and we're going to say a PowerPC processor has 50 magic tricks, half the number of magic tricks. And we're writing the same program for both of these processors. We compile it. The compiler needs to take in the architecture, take in the operating system, all that stuff, ultimately produces an executable. What's the executable? It's the list of the magic tricks that need to be executed on that particular processor in order to accomplish the task for the program that you wrote, right? Okay. Well, so you have two programs. Let's say the program was both of them written in C++. We wrote the same C++ program. We compiled it once for Intel architecture, which is going to produce a solution in terms of those 100 magic tricks. Then we compile that same source code again, targeting the Mac operating system and the PowerPC architecture. So now it has produced, from that same initial C++ code, a different set of low-level instructions that are a subset of those 50. So it had half of the magic tricks to work with to come up with the same solution. Pros and cons. What's good about RISC? Go ahead.
Sometimes it can be faster and more efficient, depending on the program.
Which can be faster?
RISC can on selected condition speed faster. If it's like the 50 magic tricks it has, that's just everything the program needs.
I get it. If the moon's aligned, and because I mean, kind of the idea is that those 50 magic tricks ultimately can solve all the same problems as the 100 magic tricks on the Intel processor. So when Intel imagines what's the minimum number of magic tricks required to solve general purpose problems, they come to the conclusion that it's 100 in our example here. Whereas the PowerPC guys say, well, we think we can do it in 50. We think we can solve the general classification of problems with less magic tricks, which then implies that some of those magic tricks might do a little bit more. Kind of that example from earlier when we were talking about that they kind of combined magic trick X and Y with second magic trick Z in a new processor to give you an XYZ magic trick, because they're often used together. So if the moon's aligned, you could have potentially a higher performance thing because you have less instructions going into the same solution, which ultimately then produces a faster solution since it's all hardware without having to process more than one instruction. Okay? So we can say possibly faster, but very situationally, right? Okay? Yeah. Okay. What else? Actually, I don't know if it would ever be slower. At least not for the same reason. I think I think you would ultimately get solutions that would run faster on the processor because it's still running through hardware with less instructions. Which aspect would actually be slower?
If it needed to do 2 of its magic tricks to perform 1 of the 100.
But it's actually only 1 magic trick on the RISC. It's just a fat magic trick.
But if it can only fit 50 select certain ones, I'm saying if it's one that they didn't select as their 50.
But that's only, so you're saying it might be missing a magic trick.
Yeah.
Well, then all of a sudden we're saying that processor really can't solve general purpose problems. So now we're saying it's no longer a general purpose processor. I think it's reasonable to assume that both processors could solve the general classification of problems. Just a RISC processor did it with less magic tricks because it combined magic tricks together. So you had to play by the rules of that processor. Who produces the low-level code? When we have our C++ program, and that's a high-level program, right? Okay. How does your low-level code actually get produced? Compiler. So how hard is it? How much extra work are we putting in on the compiler to output RISC code compared to open architecture code? Quite a bit. And what made it even harder than that? So we're gonna right off the bat, we're gonna say if you have to take the exact same input code, exact same source code, and we're gonna produce an output based on 50 instructions versus based on 100 instructions to work with. To identify those 50 instructions correctly in an optimal way is going to be a harder task. Writing that compiler is going to be a more complex problem to solve. That's a hard compiler to write. We might also then say that the chances of it getting a truly optimal solution might be relatively low, or as optimal as having more granular control over the magic tricks. Because now you're having to say, okay, well, I really need a magic trick that just does A and B. I have a magic trick that does A, B, and R. I'm going to use A, B, and R, but then back off the R, requiring another magic trick, which might be an example where it could be slower then. So all of a sudden you have a processor that makes sense in principle. Like, why can't we reduce the number of magic tricks to solve the general classification of problems? But when it came to the players that are involved in creating source or creating an executable that works for that processor, you were producing executables that either with significantly more time, with probably with probably less optimization, just to get an output on a processor that was arguably faster because it had less heat issues and could probably run at higher clock rates, stuff like that. But maybe was its own worst enemy, something like that. So RISC, we would say hard to write compiler for, something like that. Open architecture, possibly slower, easier to write compiler. We might say for a RISC, more energy efficient, less energy efficient. So now when we make a comment like hard to write a compiler for versus easier to write a compiler for, does that mean you can't write a compiler for it? No, you could still do it, and you could even make one that produces optimal code. It's just a much harder task to do. So in the moment when Apple was running PowerPC processors, what time are we at? 25? Okay, good. So when Apple was running PowerPC processors, which were RISC, and PCs were running Intel or AMD processors, which were open architecture, non-reduced instruction set processors. Now you have executable code in that moment that actually was more optimal on the open architecture, at the cost of probably being at least as fast. So maybe that gap was closed. We said RISC possibly could be faster, but open architecture is probably more optimized. So at the end of the day, maybe it's a wash-ish, something like that. Not because RISC couldn't have been more optimized, just at the time it wasn't. So performance-wise, maybe we just kind of give them, sometimes you win, but for kind of different reasons. And that had to do with the evolution of the compilers that were written for it. Back then, we were only thinking about computers that were hooked to the wall. That's not what we think about anymore. Now we care about battery life. So when Apple went away from PowerPC processors, this was right after, their company almost failed. Steve Jobs came back. They switched to Mac OS X, but still for PowerPC, which kind of saved them from a multitasking operating system was crappy, even though Mac users said it was the best operating system ever with OS 9. It fixed their operating system problem. And then a year later, Apple turned around and said, by the way, we're going to yank your processors you've been using forever and move to Intel. So now all your applications that used to work don't work anymore with your new Mac you just bought, because they were compiled for PowerPC for a reduced instruction set processor, where now you have an open architecture Intel processor. So then there was a whole wait for all the applications to be ported over to Intel. But it worked out for Apple. You had a company that was right on the line of failing as a company. By most companies in the same position would have failed. They just happened to have somebody with Steve Jobs' pockets come back and was willing to make payroll. So there's something to be said for that, I guess. And now they're the most valuable publicly traded company in the world. I think they're losing some of their shine these days, but regardless, they're money-wise, they're doing all right right now. But in any case, when you look at this comparison between reduced instruction set and open architecture, the thing that stands out the most to us today is this energy efficient aspect of this. We've already been having this discussion today about how processors keep getting faster and faster and faster, or at least more and more capable. So if they're not getting faster clock speeds, we're picking it up with more cores or optimal cores or more magic tricks or whatever it is. Well, now, if we're starting off with the idea that, okay, well, we have the capability of making processors today using pretty high standards with 9 nanometer technology and stuff like that. What if we now go back and revisit this idea of reduced instruction set processors? Because this whole memory efficient thing, or more energy efficient thing rather, is something that is pretty important to us today. We have the power and the speed and things like that we need. Now we want the whole battery life, where we're going to have a cell phone that will, run for, a month without charging. One of these days we're going to have that. You're going to have little atomic, reactors inside of your nuclear reactors inside of your phone. Did you keep that in your pocket?
No.
Yeah.
That depends. I'll take it to lead around there.
Well, it's probably going to be made by Tesla. It'd probably be all right.
Probably.
Yeah, probably. But your phone you'll never have to charge your phone again. What if you had that option today?
I'm not sure I would take it.
You never have to charge your phone again. We're using too much energy for that. Okay, so now we've had this return of our reduced instruction set architecture, and that has come back in an architecture called ARM, ARM. So in our book, we're going to be talking about the instruction sets dealing with ARM. All right. Remember, Bible homework is up. It's due by midnight on Sunday. If you haven't already gotten the book, get it. And I will see everybody on Monday. And you better hope it doesn't rain over this weekend, because my golf course is closed again today. And if I don't get to play golf sometime between now and next class, we will almost definitely have a quiz.
I can see you on Monday. Something's wrong. Also, by the way, your account was locked out. You should have access to it.
Why was it locked out?
I don't know. You locked yourself